Swayam Prabha. Digital India. Educated India.
Welcome you back. In the last lecture, what we have seen that how to find out the Fourier series or Fourier cosine series or Fourier sine series of a particular function. And also in the last lecture, we have seen that if the Fourier transform or Fourier cosine transform or Fourier sine transform of a function is the function itself, then we call the function as a self reciprocal function. And also we have proved one more thing, that Fourier transform of a function is equals to the Fourier cosine transform of a function. That means Fourier transform and Fourier cosine transform of a function are always same. So, let us recap these things with one more example. Let us see this thing, f x equals 1 when x mod x less than a and 0 for mod x greater than equals a. Let us see it once more. So, from here actually we have to prove one more thing also. Here a is a positive real number, and then we have to find out, prove that 0 to infinity sin t by t dt, this is equals pi by 2. So, let us start with this one. The given function is f x equals 1 whenever x lies between minus a to a, because we have seen that if mod x less than a, then the value of the function is 0. That means, for minus a to a, the value of the function is 1 and it is 0 otherwise. It is 0 otherwise. So, Fourier transform of the function f x, Fourier transform of the function f x, this is equals from the definition, which is nothing but capital F alpha, we write down. This is equals to 1 by root over twice pi minus infinity to infinity f x into e power I alpha x into dx. This is equals 1 by root 2 pi, value of f x is 1 from the given function. So, this simply minus infinity to infinity will be reduced to minus a to a, because in all other ranges intervals the value of the function f x is equals to 0. So, it is 1 into e power I alpha x into dx, and this is equals to, if you just evaluate the integral, 1 by root over twice pi into e power I a alpha minus e power I a alpha minus e power minus I a alpha divided by this I alpha will come, where the limits will be from minus a to a. So, if I substitute this value, this will be equals to 1 by root over twice pi. This simply will become, sorry, this already I have substituted the value, then only I am getting I a alpha e power I a alpha minus e power minus I a alpha. So, this limit already I have substituted and I got it. So, this e power I can write down twice I into sine of a alpha divided by I alpha, and this is equals, again this equals, I can write down root over twice 2 by pi into sine of a alpha divided by alpha. So, this is say one result we are getting. So, what is happening? Fourier transform of f x is equals to, we are obtaining root over 2 by pi sin a alpha by alpha. Now, if you take the inverse Fourier transform on this, in that case you will obtain f x. So, f x you can write down 1 by root over twice pi minus infinity to infinity f of alpha, that is the Fourier transform of the function f x into e power minus I alpha x into d alpha. Now, already we know what is the Fourier transform of the function. So, if you substitute that thing, you will obtain 1 by root over twice pi minus infinity to infinity root over 2 by pi into sin A alpha by alpha, because value of f alpha, that is the Fourier transform of the function, is root over 2 by pi sin A alpha by alpha, which we got just now, and this e power I can break it into cos of alpha x minus I of sin alpha x into d alpha. So, this value of f alpha, this particular value we have substituted from the equation 1 over here. So, this if I simplify it, I will obtain, I can make two different integrals, minus infinity to infinity sin A alpha, sin of A alpha by alpha into cos of alpha x d alpha minus I by pi minus infinity to infinity sin of A alpha by alpha into sin of alpha x sin of alpha x into d alpha. Now, you see this integral, this sin of A alpha by alpha into sin of alpha x, this particular integral, this is an odd function and this is odd function, whereas this is your even function. So, therefore, this second integral will vanish, since the integrand is an odd function, and the first integral we can write down 0 to infinity 2 into 0 to infinity, because this is an even function. So, from the properties of the definite integral, the second integral will vanish, because this is an odd function, and the second one you can write down 2 by pi minus infinity to infinity sin of A alpha by alpha into cos of alpha x into d alpha. So, we are obtaining this because of this thing, because this is from 0 to infinity, this is not minus infinity to infinity, this will be from 0 to infinity, because this is even function. So, this function we can write down 2 into 0 to infinity. So, you are obtaining 2 by pi 0 to infinity sin A alpha by alpha into cos of alpha x into d alpha. So, therefore, this value of the integral, now you can write down 0 to infinity sin of A alpha by alpha, sin of A alpha by alpha into cos of alpha x into d alpha. This will be equals to pi by 2 into f x. The function is this from here. Now, if we put x equals 0, you put x equals 0 over here, then you will obtain 0 to infinity sin of A alpha by alpha into d alpha. This will become 1, and the value of the function at 0 is 1, therefore, this will become pi by 2. Now, I have to find out basically 0 to infinity sin t by t format. Since I have to find out sin t by t format, therefore, I can put that t equals say A alpha. So, that your this gives you alpha equals t by A, or this gives you d alpha equals dt by A, and your t approaches 0 as alpha approaches 0, and t approaches infinity as alpha approaches infinity. So, limit will remain same from value, limit of t will be from 0 to infinity. So, 0 to infinity. Now, this will become sin t by t. This a will be cancelled over here. So, sin A alpha t by A. So, sin t by alpha equals to t by A. This A will be cancelled from dt by A, this thing. So, sin t by t dt, this is equals to pi by 2. So, which completes the proof of that 0 to infinity sin t by t dt, this is equals to pi by 2. So, just let us see it quickly. Once we are obtaining this, the given function was f x equals 1 for mod x less than a and 0 for mod x greater than This I am writing as f x equals 1 when x lies between minus a to a, because for mod x less than a this is 1, otherwise 0. So, f x I am defining like this way. From here Fourier transform of f x I am writing in terms from the definition 1 by root 2 pi minus infinity to infinity f x e power I alpha x dx, and this will be only from minus a to a, value of f x is 1. In all other intervals the value is 0. So, I am rewriting the integral as minus a to a. Then I am just evaluating the integral and substituting the limits. I will get this integral. This I can write down in the form of sign like this. So, once I am getting this one, that this is the Fourier transform of the function f x. This was the first part of the problem. Second part of the problem is to evaluate the value of the integral 0 to infinity sin t by t dt. For this one I have to take the inverse Fourier transform of this equation 1. So, from here f x equals I can write down by Fourier inversion formula 1 by root 2 pi f alpha into e power minus I alpha x into d alpha, and this I am writing substituting the value of f alpha from equation 1 means Fourier transform of the function, and e power I am writing in terms of cos and sin. Then I am breaking these two into two integrals. If you see the second integrand, the integrand of the second integral is an odd function, whereas the integrand of the first integral is an even function. Therefore, second term will vanish, and the first term I can write down minus infinity to infinity the integrand as 0 to infinity 2 into 0 to infinity. So, this is an odd function, and for the second one I am getting 2 by pi 0 to infinity sin alpha x cos alpha d alpha. So, that from here I can write down 0 to infinity sin a alpha by alpha cos of alpha x d alpha equals pi by 2 f x. If I substitute x equals 0, I will obtain the value of an integral sin a alpha by alpha d alpha equals pi by 2. At x equals 0, value of the function is 1, but I have to find out the value of the integral 0 to infinity sin a t by t sin t by t. So, I am substituting t equals a alpha, so that d alpha I can obtain. Also, the limit of t will be from 0 to infinity, because as alpha approaches 0, t approaches 0, and alpha approaches infinity means t approaches infinity. So, from here you can tell 0 to infinity sin t by t dt equals pi by 2. So, this completes the proof of the example. Now, let us come to the certain properties of Fourier transform. We have written three properties: Fourier transform, Fourier sine transform, and Fourier cosine transform are linear. What is the meaning? This same thing you have observed for Laplace transform also, that is Fourier transform of a f x plus b g x equals a into Fourier transform of f x plus b into Fourier transform of g x. Similarly, Fourier sine transform of a f x plus b g x, this is equals to a into Fourier sine transform of f x plus b Fourier sine transform of g x, and Fourier cosine transform of a f x plus b g x equals to a into Fourier cosine transform of f x plus b into Fourier cosine transform of g of x, where a and b are the real numbers. Let us take up the proofs one after another. Let us take the first proof, that is Fourier transform of a f x plus b of g x. This is equals, from the definition of Fourier transform, this I can write down 1 by root 2 pi minus infinity to infinity a f x plus b g x into e power I alpha x dx. Now, I can break it into two integrals. This is easy: a by root 2 pi minus infinity to infinity f x into e power I alpha x dx, plus this b will come outside. So, I can write it b by root over 2 by pi minus infinity to infinity g x into e power I alpha x into dx. Now, you see this integral minus infinity to infinity f x into e power I alpha x dx, this is nothing but from the definition of Fourier transform, it is the Fourier transform of f x. So, therefore, I can write down a into this 1 by root 2 pi minus infinity to, I am just writing 1 by root 2 pi minus infinity to infinity f x into e power I alpha x dx. This is nothing but from the definition Fourier transform of f x. So, I can write it as a into Fourier transform of f x. Similarly, if you see the second integral, here also 1 by root 2 pi minus infinity to infinity g x into e power I alpha x dx, which is nothing but the Fourier transform of g x. So, that you can write down b into Fourier transform of g x. So, this completes the proof of the first part, that Fourier transform of a f x plus b g x equals a into Fourier transform of f x plus b into Fourier transform of g of x. Let us say quickly. So, here for the first proof, as I told you, Fourier transform of a f x plus b g x, this from definition I am writing this into e power I alpha x integration over minus infinity to infinity, break it into two integrals. One is minus infinity to infinity f x e power I alpha x dx plus b by root over twice pi minus infinity to infinity g x into e power I alpha x, and the first integral is nothing but a into Fourier transform of f x. Similarly, the second integral is nothing but the Fourier transform of g x. So, this completes the proof of the linearity property of Fourier transform. Now, let us see the second one, where we are saying that Fourier cosine transform of a f x plus b g x equals a into Fourier cosine transform of f x plus b into Fourier cosine transform of g x, or the sign you can take. So, on the same way, basically if you see whatever I was telling you, up to this, once we have done this thing, then I can tell that similarly we can prove, similarly we can prove the, we can prove the 2 and 3, this thing also on the same way. I am not giving you the proof of these 2 and 3, because 2 is your Fourier cosine transform of f x plus a Fourier cosine transform of f x plus b Fourier cosine transform of g x equals a into Fourier cosine transform of a x plus b into Fourier cosine transform of g x. So, on the same fashion I can tell that similarly we can prove the second part also, that is we can prove that similarly the second and third part on the same way we can prove. So, I am not proving the second part and third part, because these are similar and you can do it of your own. Now, let us come to the next theorem, that is shifting theorem. Fourier transform of f of x minus a equals e power I a alpha into Fourier transform of f x, that is capital F of alpha, where f of capital F of alpha is nothing but Fourier transform of f x. The shifting theorem was there in Laplace transform also, that is if you are shifting from the x to x minus a, then one e power exponential power is being multiplied, that is e power I a alpha into Fourier transform of f x. Let us see how we can prove this one. We are starting from the left hand side, that is Fourier transform of f of x minus a, this is equals 1 by root over twice pi minus infinity to infinity, from the definition f of x minus a into e power I alpha x into dx. Now, I have to change it to t, say. So, I am substituting t equals x minus a in this. Once you are substituting t equals x minus a, so the limits of the integration as x approaches minus infinity, t will approach minus infinity. and when x approaches infinity, t will also approach infinity. F of x minus a, this will become f of t then. Here it is e power I into alpha into x is there, x is nothing but a plus t, and dt will be replaced by dx will be replaced by dt, since dt equals dx. So, therefore, by substituting t equals x minus a in the given integral, I am obtaining this, and this equals this e power I alpha a, this is independent of t and which I can bring outside. So, e power I alpha a, if I bring it outside, 1 by root 2 pi minus infinity to infinity, this is your f t into e power I alpha t dt. And if you look at it, 1 by root 2 pi minus infinity to infinity f t into I alpha t dt is nothing but the Fourier transform of f t, that is f of alpha, we can say. So, this is equals, you can write down e power I alpha a into f of alpha, where f of alpha is the Fourier transform of the function f x. So, which completes the proof of the shifting theorem. So, let us see this thing once more. So, here it is, we have to prove this. So, from the definition of Fourier transform, we are writing Fourier transform of f of x minus a equals 1 by root 2 pi minus infinity to infinity f of x minus a into e power I alpha x dx. This is equals, substitute t equals x minus a. So, that this equals 1 by root 2 pi minus infinity to infinity f t into e power I alpha into a plus t dt. E power I alpha a is constant term independent of t, so that you can bring outside the definite integral. So, this equals, you can write down e power I alpha a by root over 2 by pi minus infinity to infinity this integral, and which is nothing but Fourier transform of f x. So, this equals e power I alpha a into capital F of alpha, where capital F of alpha is the Fourier transform of f x. So, this completes the proof of shifting theorem. Next theorem is Fourier transform of e power I a x into f x equals capital F of alpha plus a. That is, whenever you are multiplying by the quantity e power I a x, the function f x, then Fourier transform shifts from alpha to alpha plus a. That is, if Fourier transform of f x is f capital F of alpha, then Fourier transform of e power I a x into f x will be equals to f of alpha plus a. Let us see the proof again. For these things, it is always better if you start with the left hand side, that is Fourier transform of e power I a x into f x. This is equals to 1 by root 2 pi minus infinity to infinity e power I a x f x. This is the value of this into e power I alpha x into dx. This equals, I can write down 1 by root over 2 by pi minus infinity to infinity f x into these two term. If I add, then it will be I into alpha plus a into x. If I just add these e power terms, so it will be e power I into alpha plus x into dx. Now, see this integral. Here basically your alpha is alpha plus a. So, from the definition of Fourier transform of f x, this is nothing but the Fourier transform of f of alpha plus a. So, because here your alpha is replaced by alpha plus a, so that we complete our proof over here, that Fourier transform of f of Fourier transform of e power I a x f x, this is equals to Fourier transform of alpha plus a. Again, let us see quickly here. Fourier transform of I a x f x, you are writing like this, and from here I am just combining the e power form, and which is nothing but the Fourier transform of alpha plus a. The change of scale property for any non-zero real numbers, I have written 3 if you see, where a is a real number, Fourier transform of f of a x, that means earlier you was adding, now you are multiplying by some non-zero number to the x, then this will be equals to 1 by absolute value of a f Fourier transform of alpha by a. Similarly, for Fourier sine transform of f of a x equals, I can write down 1 by a Fourier sine transform of alpha by a is greater than 0, and Fourier cosine transform of f of a x equals 1 by a Fourier cosine transform of alpha by a. So, again let us come to this one. So, that proof of 1, I am assuming that a is greater than 0, then Fourier transform of f of a x, this equals 1 by, I can write down 1 by root 2 pi minus infinity to infinity f x into e power I alpha x into dx. Now, if you substitute here t equals a x, then this will be replaced by 1 by root 2 pi minus infinity to infinity, this will be f t into your x is t e power I, sorry, this was f of a x, I have written wrongly, this will be f of a x, because here it is f of a x. So, that is reason f of t will be coming e power I alpha t by a into dt by a, by substituting this, and this is equals 1 by a if you bring it outside, f t into e power I into alpha by a by t, basically I into alpha by a into t, and this means this will be the Fourier transform of f of alpha by a. So, this is the first part when a is greater than 0, because we have assumed over there that modulus of a we have written. So, for a greater than 0, I am showing that Fourier transform of f of a x equals 1 by a f of alpha by a. Now, see, whenever you assume now a is less than 0, then Fourier transform of f of a x, this equals, you can write down minus 1 by root 2 pi, because a is less than 0, minus infinity to infinity f t into e power I alpha t, on the same way I alpha t by a into dt by a, we can write down whenever a is less than 0, and which is nothing but minus 1 by a Fourier transform of alpha by a. So, therefore, you can write down Fourier transform of f of a x. In the when a greater than 0, you are getting 1 by a Fourier transform of alpha by a. Whenever a is less than 0, you are getting minus 1 by a Fourier transform of alpha by a. So, you can write down 1 by modulus of a into Fourier transform of f of alpha by a. So, the first one we have completed the proof. Just let us see, this was the 3 cases was there. The first case we have proved over here, the first case we proved this thing, this one we have proved, and on the same way these two also, in the same way if you proceed, you can prove that Fourier sine transform of f of a x equals 1 by a Fourier sine transform of alpha by a for a greater than 0, and Fourier cosine transform of f of a x equals Fourier cosine transform of alpha by a for a greater than 0. So, you can check it of your own. I am not giving the proof of this. Thank you.